In computer science, we often deal with ways to organize and manage data efficiently. An abstract data type, or ADT, provides a high-level view of how data is organized and accessed, without revealing the specific implementation details. This abstraction simplifies the design process and makes our code more manageable. One such ADT is the stack, which follows the last in first out, or LIFO principle. Imagine a stack of plates. You can only add a plate to the top and remove a plate from the top. The last plate you put on the stack is the first one you take off. This is the essence of the LIFO principle, which governs how data is inserted and removed from a stack. The stack ADT is defined by its operations, not its underlying implementation. The two primary operations are push and pop. Push adds an element to the top of the stack, while pop removes and returns the element at the top. These operations are what define the stack ADT, regardless of whether it's implemented using an array or a linked list. A stack can be visualized as a vertical structure with one open end. The bottom of the stack is considered its base, while the open end is the top. When we add an element, it gets stacked on top of the previous elements. Similarly, when we remove an element, we take it from the top. Encapsulation is a key principle in software development that promotes code organization and maintainability. In the context of a stack, encapsulation means hiding the implementation details of the stack from the user. The user interacts with the stack through a well-defined interface, using functions like push and pop without needing to know how the stack is internally structured. Let's dive into the practical aspect of creating a stack ADT in C. We'll use an array to store the stack elements and define a structure to represent the stack itself. Our stack structure will include an array to hold the elements and an integer to keep track of the top element's index. First, we define the structure for our stack. This structure will contain an array to hold the data and an integer to keep track of the top of the stack. Typedef struct class stack. Next, we declare function prototypes for the stack operations. These prototypes define the functions that will allow us to interact with our stack. Void initialize stack s, int is full stack s, int value, int pop stack asterisk s. Finally, we implement these functions to provide the functionality of our stack. These implementations handle the internal logic of the stack operations. Void initialize stack asterisk s. Section 4. Practical applications of stacks. Stacks are incredibly versatile and find applications in various domains. One common use is in function call management within programs. When a function calls another function, the system pushes the caller function's information onto a stack. Upon function completion, the system pops this information to resume execution from where it left off. This mechanism enables nested function calls, a fundamental aspect of programming. Another practical application of stacks is in algorithms that involve backtracking, like solving mazes or parsing expressions. As you explore different paths in a maze, you can use a stack to keep track of your decisions. If you hit a dead end, you can backtrack by popping previous decisions from the stack until you find an alternative path. Similarly, in expression parsing, stacks are used to evaluate expressions with parentheses, ensuring that operations are performed in the correct order. Section 5. The power of encapsulation. Encapsulation is crucial when designing and implementing ADTs like the stack. By hiding the implementation details and providing a well-defined interface, we enhance code maintainability and reusability significantly. Think of encapsulation as building a protective barrier around the internal workings of our stack. Users of our stack don't need to know whether it's implemented using an array or a linked list. They only need to understand the interface, the push and pop operations. If we decide to change the internal implementation later, the user's code remains unaffected as long as the interface remains consistent. This separation of concerns makes our code more robust and adaptable to future changes. Section 6. Conclusion. Stacks for maintainable and reusable code. In conclusion, the stack ADT exemplifies the power of abstract data types in software development. By encapsulating the complexities of data management within a well-defined interface, stacks simplify our code, making it more manageable and less prone to errors. The last-in first-out principle governs the behavior of stacks, making them well-suited for tasks such as function call management, expression parsing, and backtracking algorithms. As you progress in your programming journey, mastering the stack ADT will undoubtedly prove to be an invaluable asset in your toolkit.